So the purpose of this video is to conclude our discussion of electron configurations by looking at the electron configurations for ions. And so what we need to understand is that as far as ionic configurations are concerned, all we're really talking about is taking what we already know and then either adding extra electrons or taking away electrons. Now, when we do this, usually what results is something that is pretty closely resembling a noble gas configuration. So take, for example, cations. When we have cations, that is positively charged ions, we are going to end up subtracting the number of electrons from that are equal to the overall charge. So if I have something with 20 electrons and it ends up being a +2 charge, we would take 2 of those electrons away and it would end up having 18 electrons. And then all you have to do is write the electron configuration for the element that has 18 electrons, which in this case would be argon. And so more often than not, what we'll find is that a filled outer shell, a noble gas configuration, will be the result of this ionic configuration. Similarly, if we are dealing with anions, that is negatively charged ions, then we need to add the number of electrons to the total to give us the total number of electrons of the ion. So if I have 8 electrons in a particular element and a -2 charge, I would need to add those 2 electrons. That give me 10 electrons in total. The 10 electrons would take on the configuration of the element that has 10 electrons, which in this case would be neon. And again, usually when we deal with electrons and with anions, we're going to deal with the result being a filled outer shell of electrons. So we can use the periodic table to the same effect, basically just moving one spot over in either direction to get where we're wanting to go. So if I'm at nitrogen here and I add 3 electrons to it, I'd go from 7 to 1, 2, 3 over 10. I'd end up with the noble gas configuration of neon. If I have sodium and I take 1 electron away, it goes from 11 electrons to 10, it takes on the configuration of neon. So all I really need to think about doing is just moving boxes over however many are in the charge. So let's take a look at this in terms of practice. So if I'm starting with calcium, calcium has 20 electrons. The +2 charge means we take 2 away. We're talking about 18 electrons now. 18 electrons takes us to the noble gas configuration of argon, Ar, or we could write it out in the complete configuration form, 1s2, 2s2, 2p6, 3s2, 3p6. For sodium ion, again, we're talking about a positive charge. Sodium has 11 electrons. If we take the 1 away, that would give us 10 electrons. That would be the noble gas configuration of neon, or in full form, 1s2, 2s2, 2p6. For chloride ion, we're talking about adding an electron. So 17 electrons in chloride. I add 1 more, that would give me 18 electrons. So again, we're talking about the noble gas configuration of argon, or in full form, 1s2, 2s2, 2p6, 3s2, 3p6. For phosphide ion, we are talking about 15 electrons in that guy. plus 3 more for the charge would give us a total of 18. And once again, we're talking about either the noble gas configuration of argon or 1s2, 2s2, 2p6, 3s2, 3p6. Now, one important note that we want to make here is that these 3 configurations all ended at the same number of electrons. Now, there's a term that we will use for this. It's called isoelectronic. And basically what it means is they are different elemental species with the same number of electrons in them. And when we go into periodic trends, there will be one trend that exists that is related specifically to these kinds of isoelectronic series. But more on that in the next lecture. Once again, transition metals are going to cause a bit of a problem for us. Because of that unique relationship between the s and the d orbitals, we're going to see that relationship is going to make the configurations for these transition metal ions just a little bit different. One thing that we always need to remember, when we are taking electrons away in terms of an electron configuration, we want to take them away from the highest energy level. So it doesn't matter about those anomalies. It doesn't matter about anything else other than if it's a transition metal, if it's anything for that matter, it's going to lose the highest energy level electrons first, because those electrons are going to be the easiest to take. They're the ones that are going to be the furthest from the nucleus. So in the case of chromium, chromium's configuration as an S1 exception is argon 4s1 3d5. When it loses 3 electrons, the first electron it loses is this one. And the reason why it loses this one first is because it is in the highest energy level. That electron's in the 4th energy level. These are in the 3rd energy level, so we're going to take them next after we take out that first one. This applies not only to elements like chromium or nickel or any of the other traditional D block transition metals, it also applies to elements like lead. In lead, our configuration would be xenon 6s2, 4f14, 5d10, 6p2. That is our configuration for lead. If we ionize that lead 2+, well, we're going to lose the electrons that are the easiest to take, the ones that are the highest in energy, the 6p2. So that part makes some sense to us. But if we take the next one, lead 4+, the other common ion form, again, for that one, we're going to take the electrons that are the highest energy level. So that means the 6s goes away. So it'd be xenon 4f14, 5d10. All of the electrons in the 6s all go away. There's nothing left over from the 6th energy level there. So that's really all for electron configurations. Again, ion configurations are generally really pretty easy. We just need to move boxes from one side to the other based upon the charge. Add a couple of electrons if it's negative, take away a couple of electrons, it's positive. If it's a transition metal, they're always going to be positive. These are always cations. We're always taking electrons away, but we have to be careful about which electrons that we take away. Make sure that we are taking them from the highest energy levels first, then going after the D or the F electrons afterward. But that's all for electron configurations. So if you have any questions, go ahead and bring those to our next lecture. Otherwise, I'll see you later. Have a good day.